I'll wait till we have 50 people in class. Right now it's
Yeah.
48. You're counting yourself and me.
Oh, okay.
Oh, okay, 50. There you go. Right. So, morning, everyone. Afternoon, everyone. Evening, everyone, wherever you are. I'm going to continue exactly where we left off in the last class. So here's what we saw, and I'm going to sort of rush through some of today's topics, and I may be faster than normal. Please bear with me because there's a lot to cover. Here's where we left off. We saw that we saw Hubel and Wiesel's model of the mammalian visual cortex. We found that the mammalian visual cortex consists of S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over groups of S cells for robustness to noise and positional jitter. We saw Fukushima's model, the neocognitron, which emulates this behavior with planar banks of S and C cells with identical response to enable shift invariance. And of these, only the S cells are learned. C cells perform the equivalent of a max over groups of S cells for robustness. And in Fukushima's model, unsupervised learning results in learning useful patterns. Later, Jan LeCun's LayNet added external supervision to the neocognitron. They still had S planes of cells with identical response, except that now you didn't have planes of cells which were identical. You had a single neuron which scanned the input. And then C planes were emulated by cells that performed max over groups of S cells and reduced the size of the S cells. This entire structure gave us what is called a convolutional neural network. So structurally, a convolutional neural network comprises convolution and downsampling layers. Convolution layers are these scanning layers composed of neurons that scan their input for patterns. These correspond to the S-planes in the Fukushima model. And then the downsampling layers perform max operations on groups of output from the convolutional layers to reduce the size of the maps. So these correspond to C-planes. Typically, S-planes and C-planes alternate, but this is not necessary. You can, in fact, have several convolutional layers in a row before downsampling, like over here. Finally, when you're done with all of these convolutional and downsampling layers, the output of the final layer here gets flattened and goes into an MLP with one or more layers, which actually performs the classification. So of these, only the convolution layers and the final MLP are learnable, and their parameters must be learned from training data for the target classification task. These downsampling layers are fixed and they're not learnable. A convolution layer consists of a series of maps shown by these little rectangles here, which correspond to S-planes in the neocognitron. We will call these feature maps or activation maps. Now, an activation map in turn actually has two components. The first is an affine map. An affine map is obtained by convolving a filter, which is basically just a set of weights for a neuron, with the outputs of the previous layer. So this one S-plane map has two components to it. There's the affine map, and the affine map is obtained by convolving all of these maps in the previous layer with a filter. And once we compute these affine maps, we apply an activation pointwise on these affine maps to get the final output of the layer. Now, so each of these planes is computed by convolutions over all of the planes in the previous layer. To see how, let's just consider the contribution of a single map from the previous layer to this current affine map. Again, this entire structure is representing only one of the maps in the current S-plane. And I'm going to use this example, mostly because I found this example on the web and it's got a nice animation. This green picture over here basically represents this orange map here, just a single orange map. And it's being convolved with this filter, which represents the filter with which this map is convolved to obtain its contribution to this one guy. So in this example, this grid represents the previous map. All of these numbers represent the values. This filter, in this case, is 3 cross 3. And so these numbers represent the filter values. The filter also has a bias, which I'm going to assume to be 0. So the filter is initially positioned on the top of the 3 cross 3 region in the upper left-hand corner of the map, of the previous layer map, as shown in this figure, here. And so these large numbers here are the values of the map itself. They are these numbers in the figure. And the small numbers at the bottom right of each cell are the numbers from the filter. Now, to compute, when you place the filter over here, you're placing it at the top left corner. So you would be computing the top left value of the output affine map. Again, this is a map from the previous layer. You're convolving it with this filter to compute the affine map for the current layer. So when you position it at the top left corner, you'll be computing the top left corner of the affine map. And the way this value is obtained is that you take a pointwise product of the previous layer map and the filter. So it's 1 cross 1, 1 times 1, and then you sum it all up. So it's 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 and so on. That sum ends up being 4. And then you would move the filter forward 1 step and perform the same computation to compute this value. And then you'd move it forward again by 1 step and compute this value. So this is the entire sequence of computations that is obtained. And this is how you get the contribution of this one map to this affine map. Now, the filter need not advance by 1 position at a time. You can actually have a stride. That's how much it advances by is called the stride. And you can have a stride that's larger, like 2. So in this case, again, if you place the filter at the top left corner, you're going to get this value of the output map. Then you'd move forward by 2 to get the next value, and then you're out of space. Then you go down by 2 and compute this guy, and then you move forward by 2 and compute this guy. So anytime you shift in any direction, you are shifting by the stride. And because we are advancing the filter 2 steps at a time, the output map is going to be smaller, as happened in this example. Now, the animation that I just showed you only the contribution of a single map to this affine map. And in fact, this map is computed simultaneously from all of these guys. So let's see how this actual computation happens a little more carefully. So I've redrawn all of these maps out here, position them flat. Yes, Chris? What's the question? No question, I assume. There was a random noise. So I've positioned all of these maps flat out here. So this first square represents this map. This one represents the last map. So these are the output of the convolution in the previous layer or the downsampling in the previous layer. This represents the computation happening in the current layer. So the actual filter, if a filter size is 3 cross 3, then the filter will have one set of 3 cross 3 weights for every map from the previous layer. And these weights are all different as shown by the color coding. So the total number of filter parameters is going to equal the size of the filter, which is 9 elements out here, times the number of maps. There's also going to be a bias, which I'm not showing. And so in terms of computation, you're going to place the filter on the top left corner of all of these maps, and then compute an element-wise product for all of these 9 times how many ever values, sum them all up, and to get this one output map. And so here's how the computation is actually going to happen, like so. You're going to go left to right in this manner. And we're going to scan through the inputs in this manner to compute the complete output map. And this would just compute the first map, the first affine map of the next layer. But then each layer has several such maps. So to compute the second map, we are going to, which is this guy over here, the previous computation only computed this first fellow, right? To compute the second map, which is this guy over here, you'd have a second filter, which is different from the first filter. And now this filter is going to be placed over these maps, and then you'd perform the same kind of computation again to compute the second map. So there's a different way of visualizing it. You can stack the maps one behind the other into a cube. So instead of arranging all of these maps one below the other, like I have over here, I can arrange them one behind the other. And when I do so, this is going to form a cuboidal structure. Similarly, I can take all of these filter maps out here, and instead of arranging them one below the other, I can stack them up one behind the other. And now the filter 2 is going to be a cuboid, a three-dimensional cuboid. And now to compute the output affine map, I'm going to place this cuboidal filter on the top left corner of the stack, and then I'm going to perform a component-wise multiplication and then add the terms up. So this is the actual computation that I'm going to perform to compute this one term. This innermost loop over here is basically computing an element-wise product between the filter and the elements of this first map, of elements of this map, and summing them up. So that's what this innermost loop is. And then I have the outer loop, which is going to perform the same operation on each of these maps and sum them all up. And this entire operation is going to give you this particular value, just this one value over here. And so now I can perform this computation, and I can repeat that computation and scan the collection of input maps to compute the entire affine map over here. So, questions? Any doubts here, guys?
So Chris had a question, and he has mic issues, so that's why he wrote it to me. So he was asking if there are any advantages of striding more than 2 plus, or having a stride more than 2, instead of just like reducing the neurons per layer as we increase in depth. And I said, like, it's a hyperparameter that you tune, but I'm not sure, like, if there are other advantages that you have. Or like,
so we will get to that. Chris, remember this question and ask me this question in half an hour, okay? Or maybe an hour. Now, so here is the pseudocode for what we just said. This highlighted portion of the loop is the bit that performs the scan. Now these X and Y indices, they are going over the input. This is the scan at each position, and then when you're scanning at each position, you are pulling out a segment, and this should have been, yeah. You're pulling, I think there is no, this one. You're pulling out a segment of the input, and then you're computing an inner product between the cuboidal segment of the input and the filter, which is also a cube, to get you the affine value at the current location. Now the outcome of this computation is an affine map. And the size of this map depends on many factors, including the size of the input maps, the size of the filter, and the stride of the convolution. And because this is the size of this guy is actually a function of many parameters, not just the size of the input map, the output map may not be the same size as the input. So let's take a look at this in a little more detail and see how we can control it. Now consider this example. Here, my input going in, which is the map from the previous layer, is 5 cross 5, and the filter is 3 cross 3. So when I convolve it, look at what happens. The output of the convolution is not 5 cross 5, it's 3 cross 3. So why is it 3 cross 3? It's easy enough to see. Let's say I have I'm striding forward by 1, right? So let's say I have a map, input map, which is size n, and let's say my filter is size m. So this region is going to be n minus m. So that means from this position on, I can stride forward n minus m times and produce n minus m additional inputs. But then I also am currently positioned right here, right? So I have to add that as well. So if my input map is size n and my filter is size m, then I'm going to get an output map which is n minus m plus 1 times n minus m plus 1. And that is if the filter is not allowed to go past the edge of the input. Now, suppose I have a stride 2. Then in the case of the stride 2, we saw that the output is 2 cross 2, is 2 cross 2. Where did that come from? So over here, going back to this image, if I have n minus m, I'm going to have n minus m elements positions ahead of me once I place the filter at the top left corner. So if I'm striding by S, then from the current position, I can produce n minus m over S possible output values. And then I also have the current one. So this one is going to be n minus m over S plus 1. So if the stride is greater than 1, you're going to end up with an output map, which is, I'm not sure why this is not working. You're going to have an output map whose size is n minus m over S. I'm showing you this rounding down because these are all integers, plus 1 times n minus m over S plus 1. So that makes sense to everyone?
So there's a question, and this relates particularly to how many output channels are created, because there was a student who asked, is there only one output map per layer? That is not right. It depends on the number of like filter channels as well, right? So can you?
So again, we'll get to this notion of terminology of channels. It's not something that I'm going to introduce for another half hour.
Okay.
But that's only a terminology. Again, this word channels is a highly unfortunate word. The correct thing to think about is the number of neurons in the scanning NLP, and the neurons are filters. So the correct way to think about it is filters. And why is it a filter? Because you have first an affine combination, that affine operation of scanning through a linear combination is a filtering operation. So it's really a filter followed by an activation. The word channel comes from a different place. We'll get to that later. Anyways. So the general situation is that if you have a stride of 1, you're going to get n minus m plus 1 on each side. If you have a stride of S, you're going to get n minus m plus over S plus 1 on each side, assuming you're not allowed to go beyond the edge of the input. And so here is the output of the size of the output. If the image is n cross n, I'm assuming everything is square. We can extrapolate it to non-square images. If the filter is m cross m, filters are usually square, and the stride is S, then the output size on each side is going to be n minus m over S plus 1. Now, if S is greater than 1, clearly this is going to reduce the output size. Even if S is 1, what happens is that when you have S equals 1, the input size was n, the output size was n minus m plus 1. So you lost m minus 1 columns and m minus 1 rows. So every time you convolve with the filter of size m, the image is going to shrink by m minus 1 columns and m minus 1 rows. And sometimes this is not considered acceptable. You want to maintain size. And so when you want to maintain size, one standard thing you would do is to introduce m minus 1 columns of rows and m minus of zeros and m minus 1 rows of zeros, but you'd split these symmetrically or as close as possible to symmetrically on either side of the incoming map. So if m minus 1 is an odd number, one side will be larger than the other. Otherwise, both sides will be the same. And you're going to add, so if you have a filter which is say 3 cross 3, then m is 3. m-1 is 2. So you want to distribute 2 columns of zeros on either side of the image. So you'd have 1 column to the right, 1 column to the left. Similarly, you'd have 1 row of zeros above it and 1 row of zeros below it. And so the outcome of this convolution is an affine map. And the actual output of the layer, we then apply an activation to every entry on this map to compute the output. Now, by the way, going back to the question about number of channels, observe that when we spoke of filters over here, I said each filter creates a new map, right? So each filter, each of these maps is what you call an output channel. You would need one such filter for every one of these output maps or output channels in your lingo. And so you'd have one such cube for every output map. We'll get back to that. I should have mentioned it at that point, but anyways. So having gone through all that, where are we? We are at slide 18. So here is the pseudocode again. After having computed the affine combination, you just apply an activation to it and compute the output maps, right? Now, the second component of the CNN is the downsampling layer. The downsampling layer occurs between convolutional layers and shrinks the maps. And the downsampling layer is also often called a pooling layer because we pool a number of neighboring values from the previous map to compute the downsample value from it. And the most common pooling, of course, is max pooling. So here's how we perform max pooling. If you have, after a convolutional operation, suppose you had a map of this kind for one of these neurons, then at each position, we look at a small window around that position and select the largest element from it and replace. So let's say you're looking at the top left. You look at a small window around it, select the largest element and replace this top guy, this corner guy, with this one. So this is your max pooled value. And this is how you'd actually perform your max pooling. At each position, you're going to look at a small square window starting from that position. Pick the largest value and retain that for the output. And so this is what the max pooling will do. You operate on an incoming map and you get a max pool map. Now, striding in this manner doesn't really give you downsampling because now the output map is going to be almost the same size as the input. So to obtain downsampling, the max pooling will require a stride greater than 1. So typically, you pick up the max from the small window, then you stride forward by more than 1 column, and then pick up the max and keep doing that. And so when you stride down, you'd stride down also by more than 1 column. And as a result of all of this striding down, the output map is going to be shrunk with respect to the input by a factor that's equal to the stride in every direction. So here, the output is going to be, because the stride was 2, the output map is going to be half as long, half as wide, and half as high. It's a factor of 2 shrunk, both in terms of height, width, and in terms of height. So again, pseudocode for max pooling. I won't actually get much into pseudocode today because we don't have time, but please look at the pseudocode in the slides. You're going to need it for your homework. The key thing I want to point out is that max pooling is performed independently. The convolution, in order to produce one affine map, you looked simultaneously at all of the maps in the previous layer. To compute a max pooled map, each max pooled map is going to be obtained from just one convolutional map in the previous layer. Now, in general, if you downsample and you start off with an n cross n image map, and if you're pooling with a p cross p pooling filter with some stride d, then the output is going to be n minus the, same thing. It's just like the convolution. So the output maps is going to have a size which is n minus p over d plus 1. And typically we want actually zero that during downsampling. Now, instead of computing the max of these guys, the reason we are computing max is we're just sort of emulating what we believe mammalian vision to do. But then mathematically, there are other operations you can perform, which are not max. And can you think of what else you could do over here? Anyone? Instead of max?
Summation.
Summation or averaging, same thing, right? So you can actually have a mean pooling, in which case you'd be taking the mean. So here, if I were performing max pooling with a stride of 2, I'd have one window here, one here, one here, and one here. And the output is going to be the largest of these 4 regions. That's what this color-coded image shows. 6, 8, 3, 4. Instead, I could take the means of these 4 regions, and I'd get a different output. Or I could, so that's the mean pooling pseudocode. Or I could compute the p-norm, which we don't need to get into what the p-norm actually is, but there are other operations you can perform, which is some function computed over these inputs. In this case, I've got a p-norm. And as a matter of fact, instead of having even a max or a p-norm, you could actually have a neural network which decides how best to combine all of these guys to compute its output, to compute the downsampled value for this window. And in that case, the same neural network, the neural network's fixed. It's just scanning the input and it's producing the output. And once I begin scanning the input, what does this look like? Anyone? What does this look like?
Convolution.
It's just a convolution, right? So when you decide to move away from biology and just go into the simple computational aspect of it, it turns out that even the max is not necessary. You can just have a neural network. Or what you can do is you can get rid of this entire downsampling operation altogether and simply have a standard convolution with a stride greater than 1. And that's going to give you downsampling for free without explicit downsampling. And now the specific operation that you're using for downsampling is itself learned as part of the convolution. So this is what we call an all convolutional neural network. And in fact, this tends to be a lot more popular than having explicit downsampling, for which there's really no clear mathematical justification. And it's originally based on the biology of things. So just the pseudocode, we saw pseudocode for the convolutional neural network in the last class. And this is the same pseudocode. There we actually didn't include any pooling layer. So this is pseudocode actually for a all convolutional neural network.
Oh.
So here's a, yeah.
Sorry, there are like too many questions on chat around why pooling is done, and I'm like trying to answer what I would like you to answer so that it addresses everyone. So other than reducing the model complexity, like why exactly are we pooling?
So the original hypothesis, right? Remember, so originally the reason pooling was done was we were just trying to mimic the mammalian vision. Remember the C cells? So when Jan LeCun implemented this, Jan LeCun just started off with Fukushima's model and added supervision. Fukushima's model was based on Wiesel and Hubel back in the 50s, where they said, hey, there's the C cell which is looking at groups of S cells and it's picking the max. So the motivation was biological when we actually began. But in the manner of all things scientific, you start off with some completely ad hoc process, and then you give it some reasoning. And so the reasoning that you give is, remember, when I took a small window and then scanned an input to get a bunch of maps, and then I sort of scanned this guy with a window which looked at a larger map. The reasoning we said was that we were actually creating a hierarchy of features. So for example, if I were trying to construct a flower, this first layer might be looking for substructures of a flower, like a sepal. And then the next layer is going to be putting those guys together to form maybe a flower. Now, if my sepal is shifted by 1 pixel, does that mean that the flower is no longer a flower? That 1 pixel shift should not matter, right? So within any larger pattern, if the individual subpatterns jitter a bit, that shouldn't change the composition of the larger pattern itself. Do you understand what I'm saying? Questions? So assuming not, so how do I actually model this jitter? I'm looking for some substructure, and I want to say I'm going to be looking for the substructure over here, but I don't really care if it was off by 1 in any direction, because it's not going to change the overall structure. So you look not just over here, but in the vicinity, and just pick the largest of the lot. And so this is supposed to give you some kind of jitter invariance for the lower level patterns that together compose the higher level patterns. That's why we have this max pooling. But then once we have max pooling, just sliding things with max pooling sort of stops making sense, because you're accounting for jitter already, so you can have a larger stride. Did that make sense? Whoever asked the question, raise your hand, or I'll wait. Anything on chat, Rashmi?
No, there were actually multiple people asking about pooling, so there was like not a single person who was asking.
Raise your hands that way if you got it. I can watch. No hands raised. Raise your hands. Yeah. I'll wait, right? Thank you. I'll trust you that you got it. So I'm going to sort of go through this lecture. This lecture is going to be a little more hasty than other lectures. I won't pause too frequently for questions. So here's the story so far. The convolutional neural network is a supervised version of a computational model of mammalian vision. So it includes convolutional layers comprising learned filters that can scan the outputs of the previous layer, and downsampling layers that vote over groups of outputs. Convolution can change the size of the output, which can be controlled via zero padding. Downsampling may perform max, p-norms, or be learned downsampling networks. And regular convolution layers with stride greater than 1 also perform downsampling, which eliminates the need for explicit downsampling layers. Now again, the point is, remember, we said you can replace a max by a soft max. And if you replace a max by a soft max, it's going to be a somewhat smoother and nicer version. So if I replace the max and the max pooling by a soft max, that's going to do an even better job in principle. And I can replace the softmax by any other activation. And so this jitter invariance is just not naturally obtained if you simply use a convolution with a stride greater than 1. So we sort of eliminated the immediate analogy, the biology, immediately. So let's put all of these together for a typical image classification task. And I'm going to assume max pooling for downsampling. So if you're processing images, the images could either be grayscale or color. Typically, we'll assume color. So if you have a color image, the image is going to have 3 sub-images, R, G, and B. And so the input is actually a set of 3 images. And I can stack these together just to continue using the cuboidal visualization that we saw. And so I get this cuboidal stack that is 3D. Now, our first layer will consist of a set of K1 filters in all. So the K1 just means that it represents the first layer. And each filter is going to have a face, which is this front face of some size L cross L, but it's going to have 3 planes. So it's going to be 3D. And the number of filters typically is going to be a power of 2 for purely computational reasons. the size of the face is going to be typically 5 cross 5 or 3 cross 3 or 1 cross 1. So where do these crazy numbers come from? Now, remember, we are sort of composing things hierarchically as we go through the network. So because we're composing things hierarchically, you want the face of the filter to be small enough to capture fine features within the maps at the previous layer. And so if you want them to capture really fine features, they must be small. And so we get filters of size 5 cross 5 or even 3 cross 3. But what's this crazy 1 cross 1? I mean, what is a 1 cross 1 filter? Now, we've already seen a 1 cross 1 filter before. Do you remember where we saw it? Anyone? Where was this encountered? Guys?
Someone says, is that like scaling?
No, we actually saw this in the last class, right? So when we were not performing distributed scanning, what were we doing after the first layer? So when we were not performing distributed scanning, after the first layer, each subsequent neuron only looked at one position from the maps of the previous layer. Remember? We used just these guys and computed an output, and then we scanned, looking at one position at a time when we were not using distributed scanning. Do you recall this? Guys, who recalls it? Yes. That's a 1 cross 1 filter. You're looking at one position. So that's your 1 cross 1 filter. That is a non-distributed element of your scan. So it's not that we always use distributed representation. We can also intersperse these with non-distributed layers in the middle of the network. It's simply a perceptron that operates over the depth of the stack of maps but has no spatial extent. Right. So there's supposed to be a poll at this point, right, Rashmi? Is there a poll?
You're muted, Rashmi.
Yeah. Okay, stop in 5.
Mm-hmm.
So, I mean, both are true. An all convolutional network is basically just your scanning NLP with distributed representations. And the convolutional neural network is basically just a shift invariant pattern detector. So now, although I've been representing filters as 5 cross 5 or 3 cross 3, the more appropriate notation is 5 cross 5 cross 3 or 3 cross 3 cross 3, because you have the face, which is L cross L, and then you have the depth, that is 3. So there are actually 3 numbers defining each filter. And so here are all the parameters that we would have to choose for just the first layer of the network. It's how many filters we want, K1, the size of the filters, which is the size of the face. The 3, of course, is not a matter of choice. You just have the 3 given to you plus the bias, but L has to be chosen. And then you also have to choose the stride of the convolution. Now, each filter is L cross L times 3. So it's 3L squared. Each filter also has a bias. Remember, each filter is just a neuron that's scanning the input, right? So every neuron has a bias. So it's 3L squared plus 1. This is per filter, per neuron. And then you have K1 of these guys. So this is the total number of parameters for just this one layer. Now, Of course, if you want to perform the actual convolution, you may zero pad the input according to the size of the filters, just to ensure that the images size of the images is retained after convolution. And so each of these filters is going to scan this input, and it's going to produce an output activation map. Now, there are two steps to this process, as we've seen before. First, the filter scans the input, which is this equation we've seen before, and it's going to compose an affine map. Subsequently, we're going to apply the activations element-wise to this affine map, and you're going to get the output activation map. So you're going to get one of these guys from each of these filters. Once again, these are your so-called output channels, one per filter. And so, again, to reiterate, these are all the learnable parameters in the first convolutional layer. We have 3L squared plus 1 parameters per filter. You have K1 filters. So you have K1 times 3L squared plus 1 parameters in just the first convolutional layer. Following the convolutional layer, there's a downsampling layer in our example. So it's going to look at blocks of P cross P in this output. It's going to pick the max, and it's going to create the next layer. So here is the operation for max pooling. For every location over here, it's going to look at, so if the pooling has some stride D, then for the ijth location, you're going to have to go to where you would be after I minus 1 strides in the horizontal direction, and j minus 1 strides in the vertical direction. And you're going to look at a small square region, a P cross P region, in that, starting at that point, and you're going to pick the maximum value. So this is the max pooling operation. Each max pooled map is obtained from a single activation map from the previous convolutional layer. So in the max pooling operation, here are the parameters you'd have to choose: the size of the pooling block and the stride. You also could decide between what kind of pooling whether you're going to use. Are you going to use max pooling, mean pooling, or are you even going to use pooling? That's a design choice. So if you're actually performing max pooling, then you won't actually perform this operation directly, because this operation by itself is not differentiable. We're going to have to split that operation into two steps. In the first step, we're going to find, so you would have some block over here. So when you're doing max pooling, you would, to compute the ijth location of the max pooled map, you're going to start and look at some region over here in the previous convolutional layer. So in the first step, you're going to find the location of the largest value, the index of this largest value. So first you would find the index of the largest value. And in the second step, you're going to read the value over here at that position and then copy it into this location. Now, it's not different from simply picking the largest value, but breaking it up into two steps that actually ends up being important for the backward pass.
Sorry, there's a question, and I think like students are a bit confused about why we have like K underscore 1 filters now, when we were like talking about just one filter convolving around the entire image in the previous examples.
So you have one filter. Again, you're getting confused between your code and what's happening over here, right? One filter is one neuron. Remember, in your scanning MLP. So you have, so this filter is a cube, and it's going to be scanning this, and it's going to produce this one map. This second filter is another cube. It's going to be scanning this guy and producing the second map. And so for each of these maps, each of these, which you call channels, you're going to need one of these cubes.
So basically the number of filters that we have equals to the number of output channels, right?
That is it, right? The number of maps. Again, the term channels is very unfortunate over here. In fact, again, it's more convenient to draw everything as cuboids. And in fact, I'm going to introduce the jargon right here, right? The filters, there have been so many different terminologies thrown at this problem. I have no idea why. We haven't actually stayed consistent with terminology. The filters are often called kernels. The outputs of the individual filters are called channels. So the number of filters is the number of channels. Does that answer your question? It's very convenient that this slide came up at the right place. Questions, guys?
Yeah, there's one more. Do we have something equivalent to pooling layer in distributed scanning MLP? I think they are confusing it again.
So the distributed scanning MLP is just spreading the pattern detection over many layers, right? But between any two, so think about this. A pooling layer is also just, the pooling operation is just a neuron, right? So let's say I have a distributed scanning MLP. So this distributed, I'm showing you the compact form of the distributed scanning MLP. And so we actually know that this little 3x2x1 figure actually represents many neurons, depending on so this neuron, for example, might compute a map. And if this guy is looking at some small region of this map, then this one is actually connecting to many copies of this neuron, as many copies as there are elements in the small region of the map. So we saw this in the last class. Now, at any point, if you're having a, if you're, wait a minute, so I should try to, okay, I can just continue using this. So when I do this guy over here, right? This neuron, the practical scanning MLP implementation of it is going to have many copies of that neuron. What exactly is your pooling layer? Your pooling layer is something like this. It's looking at 4 adjacent values at each time, and it has a max activation. And the pooling layer is just another neuron, except this is a non-learned neuron, layer of neurons, which has a max activation and only looks at adjacent values, adjacent in this 2-dimensional map for each guy. And then the next neuron is, the next layer neurons actually look at the output of these pooling layers. Now, again, you don't need to have a one-to-one correspondence over here. So if the first layer neuron over here is creating this map, and the second layer neuron is looking at a small region of the map over here, so let's say this is 2x2, then this second layer neuron would be looking at 4 of these guys, right? Let me make it 3x3 just so I can explain better, right? So the next layer neuron is going to be looking at 9 of these guys in theory. But then I can have a max pooling, which groups these into 3. Typically, you'd have 4 for pooling, max pooling, but assuming you have 3. And so the max pooling layer itself just becomes a layer of neurons. And the next layer neuron is actually going to be looking at the output of the max pooling layer. So this might look confusing. I should probably draw a figure for you guys and remind me to do this on Piazza, but the max pooling layer is just another component of your distributed scanning MLP. So Rashmi, can you keep track so I can draw the figure for this on Piazza?
Yeah, sure, I'll do that.
Yeah. And I don't think that if I don't assume, I assume it made no sense to you the way I drew it, but it's better explained more carefully. So now, once they have the output of the max pooling, I'm going to have a second layer of filters. I'm going to have a bunch of filters which operate on these guys. They are going to create their own output maps, each of its own. Each of those filters will have its own face. But the depth of this cuboid over here is going to be equal to the number of channels or the number of filters in the previous layer, right? So in the previous layer. So the first time it was L cross L cross 3 because you had RGB, but now you have these many maps, these many channels, if you like to call it this way. So each cube is now going to be L3 cross L3 cross L3 times the number of channels. So when you go to the next layer, the depth of these filter changes. And then you'd have some convolutions, and they have their own parameters. You're going to perform some max pooling on it. And the max pooling again has its own set of design choices, which is the size of the pooling block and the stride. And you can continue that to that for many layers. And finally, you have an MLP. Now, in general, unless you want the convolutions themselves to shrink the maps, convolutions will be performed with a stride of 1. In an all convolutional network, convolutions can be performed with a stride greater than 1. But then here is something that you have to worry about, right? So let's say I have my input, and my input has, let's assume my input is 100 cross 100, and my input has 3 colors. So how many unique values does my input image have if it's 100 cross 100 and it's got 3 colors? How many will it have? Anyone?
30,000.
30,000, right? So now suppose I convolve this with a bunch of filters. Each filter is going to compute how many outputs is the filter going to compute? Each filter, assuming it retains the size with 0 padding. How much would it compute? You're scanning this with the filter. How many values will it compute?
3.
3?
10,000.
10,000, right? 10,000. So if I want to retain all the information about the input, how many filters do I need? At least
3.
I would need at least 3 filters, because otherwise the number of output values is going to
Decrease to 10,000.
decrease and I lose information, right? And that's why I need 3 filters. But now, assuming I'm going to downsample going forward, so that now the size is reduced by half. So for the downsampling, right? How many filters do I need? Size is reduced by half in each direction. How many filters do I need? If I'm downsampling, what is this size? What is the size of the map?
50 by 50.
50 cross 50, right? So how many unique values will each output map have?
2,500.
2,500. So how many of these guys would I need to retain all 30,000 numbers?
6.
6? 12.
Yeah, 4 times.
12. Sorry.
12. So if I intend to downsample, how many filters do I need over here?
12.
12. If I intend to downsample, I need 12. So here's what happens. I can start off, I have some input, and my intention is to try to retain as much information about the input as possible at all times, right? Now, downsampling causes this issue. I'm going to start with some guy. I'm going to compute a certain number of maps. Let's not get into how many. Then I downsample it, right? So when I downsample it, this guy, when I'm done, this guy is going to have a smaller face than the original image. The only way I'm going to be able to compensate for the smaller face is by increasing the depth, right?
Diksha, could you just reiterate and talk a little bit about like why we need 3 filters? Students are again confusing it. And I guess like the easier way to just say it is like because we have like 3 input channels, we need 3 filters or more.
No, it's not just the 3 input channels. So it's a different way to think about it is, let's go back here. If I, for some reason, so I have a 10 cross 10 image. So this has 10,000 pixels, right? If I have 3 colors, this is going to have 30,000 numbers, right? So if I want to retain all the information about this image, at every time I need to have at least 30,000 numbers, otherwise I have lost information about the input. Does that make sense?
But you just said each filter is a cube, right? It has a depth of 3.
The filter has a depth of 3, right? And the filter is this cube. Yeah.
So why we need a 3? I mean, if it is a cube, then it get all the information from 3 channels.
It gets one number for this entire location, right?
Yeah.
Just think of, right? So does that mean you have kept information about every possible value within that cube, or have you just integrated it and got one number?
You got a 1 number.
So has it retained all the information? You integrated it, right? You lost it. You got W1 x1 plus W2 x2, Wn xn, where these x's are all the elements within this cube and the w's are the filter. So that is the first value that you got, correct? So
Yeah.
y has only got this value, has integrated everything out. You've lost information. So how many such different combinations will I need to get such that the set of y's retains information about all of the x's? How many will I need?
3, yeah.
As many as I have n's, right? As many, I mean, basically for this one, basically when this guy scans, it's going to create one 10,000 sized map. I've lost a factor of 3 in information, so I'm going to need 3 filters. That make sense?
I think the confusion arises from the fact that in the previous slides we were talking about like filter, like the filter size is L cross 3, and 3 are like the number of channels again in the filter.
So
and
3
right
is,
now, I guess
so that they're the same thing, right? All we are saying is the filter, again, going back to this image, this filter is, why do my pictures disappear? This is extremely annoying with OneNote. So sorry for redrawing it again and again. The filter is 3 cross 3, but it is related in the sense that the filter must be depth 3 because there are 3 channels. But also, when the filter scans, it's producing only one map. So basically, it's getting the equivalent of one face, correct? It took in 3 faces and produced one face. So in other words, you've basically gotten 1/3 because there were 3 faces over here, and this is just 1. The number of values you got was 1/3 as many as the total number of values over here for one filter.
I mean, if that's the case, why we need 3? Why we need the filter to be depth of 3? Why we just create 3 filters and then scan each channel separately?
So if you scan each channel separately, you're losing. Remember, go back. And so what we were doing was we were trying to scan this guy simultaneously from each one, right? You're trying to capture, again, what was this? This was like saying you had a multi-layer perceptron and you're combining all of the information from the previous layer. Each of these maps came from one of the neurons in the previous layer, right? If I'm only scanning locally, that's like having a network of this kind with no cross connections. Make sense?
I feel that students are still confused about the fact that we are just showing that one output map, but in fact we have like the number of output channels equal to the number of input channels. Sorry, number of filter channels.
Yeah, but again, that one output map is the output of this one neuron out here. Remember, we were scanning the input with some network, right? So if you're scanning the input with one network, we just reordered the computation going back all the way 2 classes ago. This class is not going to end on time. So if you go back 2 classes ago, let's go right back to the beginning. I mean, we have to clarify this. We had this input. We wanted to scan for a flower. So what we wanted to do was to scan this network with an MLP, right? In regions of, in some block. And so we said we can reorder this computation, and this first neuron is going to create a map, this first neuron is going to create a map, this third neuron is going to create a map, and this guy, in order to figure out whether there was a flower in this location, it looked at this position and this position and this position and took a decision. Do you remember this?
Yeah.
Right. And so it can create a map by scanning this, but when it's scanning, it's simultaneously looking at all three maps. You remember that?
Yes.
Right. So now what happens? If these three maps are basically, now if I've got a depth over here of this kind, then these three maps, if this, to retain as much information as this original image has, each of these three maps I must have at least, I hate OneNote. So we need as many, okay, close. So if there are 30,000 numbers over here, the maps produced by these neurons are 30,000. Unbelievable. What is happening here? I waste half an hour every day just trying to deal with OneNote and stupid Zoom. Okay. So again, think about this as scanning, right? If you're trying to scan, you see how these values are computed. But then another thing that you want to do is that you want these three neurons by themselves to retain all the information about the set of values that they're looking at about the window. So ideally, you're going to need as many neurons over here as the, I give up. I didn't even touch it. Guys, I'll take this off on Piazza, okay? I'm not going to be able to draw anything on this miserable device.
Okay.
It's just not. I can spend the next half hour just pulling up OneNote and killing it again. It's just, somebody's got to go and beat up somebody in Microsoft. Anyway.
We have a poll.
Yeah. I'm going to try this useless. Yeah. So. Driver. I don't believe this. Just open a notebook, damn it. Whatever X. All right, I'm hoping that this thing will not misbehave. So again, I'm going to try to answer that question one last time, and you're going to have to stay with me a few minutes after class. I'm way over on this class, way over. So here is what happens again. As you go through the network, you want to retain, you get the idea of how maps are formed and they're scanned, right? So each filter is going to compose one map. But then if you want the final classification, ideally the network is sort of taking the space of input and sort of unwrapping it so that you get linearly separable classes at the end. So if you want to make a proper decision about the input, you want to retain all the information about the input all the way to the end until you can perform classification. Does that make sense to you guys? You
Yes.
just want to wart the space. You don't want to throw away information, right? So now this one has n cross n. If the image is size n, it's got n cross n times 3 numbers. So at the end, when all of the first layer neurons have done their computation, the total size of the maps you must contain, this must have 3n squared values also. If you don't have 3n squared values, some information has been lost in the first convolutional layer. Does that make sense?
Yes.
Yes.
Okay. Each filter is only going to produce an n cross n output.
Yes, and this is reduced with stride, correct?
And that is going to, if you reduce it with stride, what will you have to do to compensate, to make sure that you have 3n squared numbers?
You would need more filters.
You need more filters. And so that's exactly what we're saying. So if you have downsampling, as you go through the network, in anticipation of downsampling, you need to increase the number of filters. That make sense?
Yes, to retain all the information, you need the same number of values.
To retain all of the information. And so typically what will happen over here, so here's Jan LeCun's network. In his first layer, he has 5 filters. He downsamples by a factor of 2, right? 4 filters, because he was just working off RGB, grayscale, and he's going to downsample by a factor of 2. So the size goes down by a factor of 4, right? Which means you need 4 filters. Make sense?
Yes.
This design choice makes sense, right? But now you have these filters. He's going to downsample again by a factor of 2. So how many filters does he need in the second layer to retain all the information?
8?
No, he's going to be downsampling by 2 on each side.
4, 4, 2, 2.
So
16.
it's 16, right? He only has 10 times, 10 in his, 10 does he? I forget the number. But to retain all of the information, now you'd need 16, and then you can downsample. That's how you know that all of these guys have all the information in the original image, just unwrapped. Make sense?
Yes.
Okay. So I'm not going to try to do anything on one note, because if I do it, it's going to die on me. So you get the idea how the whole thing works. This was Jan LeCun's original laynet. He works on images, you scan, you downsample, then scan, downsample, and so on. And eventually you pass everything to a final MLP. So end of the day, however, so you see the entire process end to end, and things that influence design choice, how many filters or how many output channels do you need, is going to be dependent, at least in part, on how much you're downsampling by, because you want to retain information. You can increase the representation, but if you decrease it, you're guaranteed to be losing information. Sometimes losing information is a good thing, because there's a lot of noise in the image, you want to get rid of it, you lose some stuff, you can reduce the number of channels. But in general, if you want to retain as much information as you can, which is the best ideal thing to be doing, as you keep downsampling, the number of filters is going to keep increasing. It makes sense to everybody? Yes, no? Raise your
Yes.
hand. Okay. So training, this is just like a regular MLP. So guys, I'm going to go at least 5 minutes over, because blame OneNote. So the only difference is in the structure of the network. Remember, eventually it just ends up looking at, if it's a scanning MLP, it's like one giant MLP. And so now you can just sort of provide examples of inputs and labels, which for images would be images in their class, Then you define a divergence between the desired output and the true output. And then the network parameters are trained through gradient descent. So the gradients parameters are computed through backpropagation. So this is the story so far. The convolutional network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, downsampling layers that operate over groups of outputs from the convolutional layer to reduce network size, and the parameters can be learned through regular backprop. So, but then let's take a look at this backprop in a little more detail. The parameters to learn over here are the parameters of all of these filters and the weights and biases for the final MLP here. And training, as we saw, is like an MLP. So we're going to be given training examples. We're going to imagine class, and we're going to be defining a loss, which is the aggregate divergence between the actual and desired outputs of the net. Typically, we'll use scale divergence. And the network parameters are trained to minimize this loss using gradient descent. And the gradients are computed using backprop. Everything is just as before. So the network is going to decide, create or come up with an output. You have a desired output, you compute the divergence between the two. And then if you had only one training instance, the loss is simply going to be this one divergence. If you had many training instances, the loss is going to be the average loss over all of the training instances. So the derivative of the loss with respect to any network parameter is going to be the average of the derivative of the divergence with respect to that parameter over the entire training set. And we're back to the old case where we need to figure out how to compute this derivative. So nothing new so far. Now, what else is not new is that you can actually backpropagate your derivative conventionally through this final MLP and use that to update the MLP parameters. But when you've backpropagated the derivative through the MLP, eventually you're going to get the derivatives of the divergence with respect to the outputs of the final convolution or downsampling layer. So what I mean is that, remember, the output of the final layer was flattened and sent through the MLP. So when you compute the derivatives backwards, you're going to get the output of the final layer, which you can sort of fold back into this cuboidal collection of maps. So just conventional backprop is going to give you the output with respect to the Ys, the activation maps of the final layer. That makes sense to everyone? Questions? Anything on chat, Rashmi?
No, nothing on chat.
All right, okay. So backpropagation now basically requires us, what happened? To transmit these derivatives backwards to compute all of these filter values. And we're going to have to make adjustments to the regular simple backprop formula. Specifically, we must now worry about how the shared computation of convolutional layers and the pooling layers affects this backprop. Now, here is the thing. For the final layer, you're going to get a final bunch of final layer outputs of the convolutional layer, final convolutional layers, and they all influence the divergence. Backprop is going to give you the derivative with respect to the output of the final convolutional layer. This is the output of the activation, right? So now we're going to have to pass that back and compute the derivative with respect to the affine maps to which the activation was applied. Then we're going to have to continue passing those derivatives backwards to the output of the previous layer. And so we want to compute given the derivative of the divergence with respect to these activation maps for one layer, we want to compute the derivatives for the affine maps for that layer, then go back and compute the derivatives for the output maps of the previous layer, and also compute the derivatives for all of the filters that were applied to these guys to compute these affine maps. So this is what we'd want to do for the convolution. For the pooling layer, you had, map-wise application of pooling if you do implement pooling. So the backprop would have finally got you the derivative with respect to these y's. You need to figure out how to pass that derivative backwards to the pre-pooling activation maps. So these are the two steps that we want to perform. So overall, here is what we need. If we've already begun our backprop, we already have the derivatives with respect to the elements of the maps output by the final convolutional pooling layer. And now for the convolution layers, given the derivative with respect to the activation y, we must go back and compute the derivatives with respect to the affine combination z. And from the derivative with respect to the affine combination z, we must compute the derivatives for the previous layer output, yl minus 1, and the weights, the filters for the lth layer. This is for the convolution layers. For the pooling layers, we have to figure out how to compute, given the derivatives with respect to the pooled maps, we have to figure out how to compute the derivatives with the maps before pooling. These are the two stages of backprop. So let's look at the convolution layers first. Specifically, just look at, given the derivative with respect to y, how do you get the derivative with respect to z? That's easy. So what happened was, remember, for each, when you're going forward, you get a collection of, first you apply the filters to the previous layer. Each filter gives you an affine map. Then you apply an element-wise activation to these affine maps and you get these activation maps. And so you just get y equals activation. Each element in y is some activation applied to the corresponding element in z. So when I'm going backwards, if I already have the derivatives with respect to y, to get the derivative with respect to z, I just have to say multiply the derivative with respect to y by the derivative of the activation function itself computed at that z. This is just a standard chain rule. So if you work your way back to y, working your way back to z is trivial. It's an element-wise operation. You just multiply the derivative with respect to y by the derivative of the activation. So this first term we have figured out. The really challenging bit is now we are given the derivative with respect to z. How do you compute the derivative with respect to the output of the previous layer? And how do you compute the derivative with respect to the filters? This is the real challenge. So we have already computed the derivative during the forward affine computation. For the lth layer, you've computed all of the maps using the output maps of the L-1th layer and the filters of the lth layer. So in the backprop, you're given the derivatives with respect to the lth layer affine maps. We have to compute the derivatives with respect to the outputs of the previous layer and the filters. And this is what we got to figure out. So again, breaking the problem down, let's first see how we can compute the derivatives with respect to the output of the previous layer. I'm going to spend a little time on this, the 5 minutes over. But it's going to be easy. This is actually fun stuff. We're going to do this with pictures, right? I have computed the derivatives of the divergence with respect to every element of every one of these maps, going backward. I want to figure out how, from these elements, I can compute the derivatives with respect to every one of the elements of every one of these maps. So in order to do this, we have to chart the dependencies. To compute the derivative for any one guy of the divergence with respect to any one guy over here, we have to see the various paths by which this one term influences the divergence, right? Now, if you consider the nth map, nth affine map, this nth affine map in Z is computed by convolving all of these maps simultaneously with the nth filter, and the nth filter has as many of these little planes as you have maps out here. So the so this is for the Lth layer, the subscript L represents the layer. W1n means that this is the filter map that you apply to the first map in the L-1th layer when you are computing the nth map in the Lth layer, right? Nth affine map in the Lth layer. W2n is the filter plane that you apply to the second map out here when you're computing its contribution to this guy, and so on. Just notation. So let me sort of redraw these with straight lines. Every one of these maps is going to be affecting this nth layer, this map, this nth map over here. And this nth map influences divergence. In fact, every one of these maps is going to be influencing every one of these guys. And they're all going to be affecting how you compute the divergence. And so, if I want to compute the derivative, say for this one guy, for the elements of this one guy, I have to compute the derivatives over all of these paths, right? But then, how does this one filter influence the first zth map? How does this one map, so the mth map in the L-1th layer, how does it influence the first map in the Lth layer? That's through filter M1. The way it influences the second map is through filter M2. The way it influences the nth map is through filter Mn. So you'd have to focus on these guys to figure out how this map influences all of these z's, and then use those and then sort of chart the dependencies out into the divergence in order to compute the derivative. So here is the complete dependency diagram for a single map. The mth map, a single map in the L-1th layer, influences every single map in the Lth layer, and each one of these maps in turn influences the divergence. So if you want to compute the derivative of the divergence with respect to the elements of this guy, I'm using a vector notation here to represent all of them simultaneously. I'm going to have to sum over all of the nth layer maps, and what I will sum is the product of the divergence of the derivative of the divergence with respect to each of these maps times the derivative of the map with respect to y. Now this order is important. This is your standard chain rule. So this is this little computation that I'm going to have to perform to figure out how to figure out the derivatives for this map y, of the divergence with respect to the elements of this map y. And so I'm going to stop right here because it'll take more time than needed. I'll pick up at this point in the next class. Any questions?
I have a question. Do we do polls right now, or do we leave it for the next class?
There's only one poll left, right?
There are 2 polls left, actually. There was at 163 and 252.
So just do the 163 poll.
Mm-hmm.
There's one final poll, guys.
Will this formula be added if the stride is like 2 or 3?
We're going to show the formula for every stride. It's got to be easy. Obviously, the answer is yes for both, right? All right. So So, okay, guys, thank you for your patience today. We'll pick up exactly at this point in the next class. And if you have any questions, transfer to the answer. Thank you. Rashmi, stop the recording.
Yep.